This lecture is about the error component model, which is used when we have panel data. So to introduce this model, let's begin by looking at the pooled regression model with panel data and see the shortcomings of this model. Our data consists of a dependent variable, yit, for n individuals going over t time periods. Just to simplify notation, let's say that we only have one explanatory variable, xit, and just to have a concrete example in mind, let's say that yit is the income of individual I at time t, while xit is the education of individual I at time t. In the simple pooled regression model, we simply set up that yit is beta 1 plus beta 2 times xit plus an error term epsilon it. In terms of explaining income, we would typically also have additional explanatory variables in addition to education. So the error term, epsilon it, would be the effect on income for individual I at time t, which is in addition to the explanatory variable. And in the pooled regression model, we make no specific assumptions about the error terms epsilon it. So let's look at some data. Very simple case. I have three individuals, 1, 2, and 3, and all three of them are observed from 2013 to 2016. The first individual has 9 years of education, second one has 12, and the third one has 16. We would typically have additional explanatory variables, but I'm just listing one. In the pool model, we make no specific assumptions about the error terms. So let's see what happens if we just assume that each error term follows a normal distribution with variance 1. So I'm just simulating errors from the standard normal distribution. Copy this down. Think of, for example, the y variable being the wage per hour. Then the error term is the adjustment on the wage in addition to explanatory variables. So what this would mean is that individual 1 at time 2013 will make 1.25 more than you would expect from this person's explanatory variables. The next year, this person will make 0.68 above, 0.26 below, and then again 0.64 above. Complete randomness among these error terms. So let's think about for a second why this is unrealistic. Individuals have characteristics that will affect the salary, but which are not measured by the explanatory variables. These characteristics could be things like being very industrious and hardworking, being intelligent, having high social intelligence, and so on. But these kind of hidden characteristics tend to remain fairly constant over time. If an individual is hardworking and intelligent in 2013, this person is likely to be hardworking and intelligent in 2016 as well. So let's call the combination of all these unobserved characteristics the individual specific effect. Let's say, for example, for individual 1, the individual specific effect is -2. Everything else the same. This individual will make $2 less per hour compared to what you would expect from the explanatory variables. Let's say that the individual 2 is sort of an average individual, so there is no adjustment either upwards or downwards in the salary. And let's just say that individual 3 is a clever and hardworking person, so this person would make $4 more per hour compared to what you would expect from the explanatory variables. We will still have some randomness over time, so we can't expect, for example, the first individual to make $2 less per hour every year. So there is still some random term. I will call this mu. and this could be completely random. So I have simulated some random values in column F. The new definition of the error term is now the sum of the individual specific effect and mu. So let's call this the new error. It is E2 plus F2. Copy this down, and we now have a much more reasonable representation of the error term compared to the one that we started with. Assuming that the error terms are completely random just doesn't make sense. It just doesn't make sense for it to jump like from positive to positive over time for the same individual. The new way of generating error terms makes a lot more sense. The first individual is a little bit lazy, so the error term is negative in every year. There is still some randomness. 2015, for example, was the worst year for this individual, making almost $2.50 less than what you would expect from the explanatory variables. The error term of the second individual is around 0, while the error term for the third individual varies around 4. So to summarize this mathematically, we want to make a model for the error term that affects individual I at time t. And we want to claim that this error term is equal to some individual specific effect which only depends on the individual. Alpha I was minus 2 for I equal to 1, it was 0 for I equal to 2, and it was 4 for I equal to 3. We still need some randomness over time, so we also add an error term mu it. This is an example of a random component model, and this parameter is called the individual specific effect. So we have for the error component model a very common model for the error term when we have panel data. Way more common than the simple method of just doing pooled or less. There are actually 3 versions of this error component model. The first version is the one that we just looked at. That's called a one-way error component model with individual specific effects. This model looks like this. The error term affecting individual I at time t is given by some individual specific effect alpha I plus some other error term mu it. Alpha I is called the individual specific effect, and the right hand side error term, the mu it, for those we typically make the Gauss Markov assumption. More about this later, but we think of them as stationary. We think of the explanatory variables as being exogenous with respect to the mu's. We think of the mu's as being homoscedastic, constant variance over individuals and time, and we think of them as not being autocorrelated. So if you like, a nice way of thinking about it is that we basically enter a formula here simulating from some distribution, and we use the fill handle. That is basically the assumption that we make on mu. We think of the individual specific effects as random as well. If I pull an individual randomly from the population, I don't know what the individual specific effect will be for that individual. But it is a characteristic that the individual carries with herself. The same idea can be applied to data that's not individual data. For example, if I observe houses over time, then alpha I could be the individual or house specific effect. So that could represent, for example, factors that affect the value of the house which is not included among the explanatory variables. So alpha I could, for example, be positive for a house that has a wonderful view. So the individual specific effect is a factor that's connected to the individual which doesn't change over time. Similarly, we can introduce a time specific effect which is connected to a particular point in time, but which doesn't change over individuals. For example, it might be the case that 2013 was a very bad year for the economy and salaries were in general lower that year. Then we would have a negative time-specific effect for each individual in 2013. So -1 for all individuals here. Maybe 2014 was a neutral year. 2015 was a pretty good year, so people would make on average $1 more per hour. And let's say that 2016 was an awesome year, $2 extra per hour. So that would be a time specific effect. The individual specific effect is constant over time for a given individual, but it varies between the individuals. The time specific effect is just the opposite. It's constant over individuals for the same time period, but it varies between different time periods. So we could have an error component model with a time specific effect, and that will then look as follows. So I have a one-way error component with a time specific effect. Then I simply assume that the error term affecting individual I at time t depends on this time specific effect gamma t, which is the same for all individuals, plus an error term which is individual specific and time specific. Gamma t is called the time specific effect, and we make the same assumption about the mu i's in this case. They are sort of nice error terms. So the final error component model consists of combining these two. I can actually create then an error term where the error affecting individual I at time t is the sum of an individual specific effect, a time specific effect, plus an error term that's specific to the individual at time point t. So this would be a two-way error component model. It's the individual specific effect plus the time specific effect plus the mu error term. For individual 1, the error term in 2013 is highly negative due to two factors. First, a negative individual specific effect, plus the fact that 2013 was a bad year. In 2016, the error term is almost zero. The great economy cancels the negative individual effect in that case. For our industrious and clever person, this person always makes more per hour than you would expect from the explanatory variables, way more in 2016. So to summarize, when we have panel data, we have a choice to make. We can make this simplified assumption that the errors are completely random over individuals and time, and then do the pooled OLS. We could assume that it's the individual specific effect that's important, so we could add that one. Or we could assume that the time specific effect is important and only add that one. In some cases, both of them are important, so we add both of them and we then have a two-way error component model.